So hello everyone, this is lecture 34 for the electricity magnetism. In the last lecture we have discussed about the reflection and the transmission, and we discussed a lot of things. And we discussed also about the Brewster's angle. So today we will study about the critical angle. So in the Brewster's angle we have seen that there was no reflection component, and the critical angle we will see that there is no transmission component. So what is the meaning of critical angle? So it is, you can remember from the total internal reflection when you study that if any ray is coming, then the reflecting wave will all contain all the energy. There will be no transmission, and that can be possible only when the second medium is rare and the first medium is denser. Because if you see that first medium is denser, means medium is rare and second is denser, means n1 is less than n2. Then what happens that after refraction, this ray will bend towards the normal, and you change any angle, it will always remain there. This component will never be neglected or the removed. So that's why we will say that if the ray is moving from the rare medium to the denser medium, the critical angle, there is no critical angle exist, because there will always be the transmission component. But see, if it is ray is moving from the denser to rare medium, then what happens? Then this ray will go away from the normal, and from here we can see that if we make at a particular angle, this ray will become parallel to this interface, and after this ray will go totally reflected, means there will be no transmission. And so that's why this angle at which it is becoming parallel to the interface, we will call that angle as the critical angle. So in the case when the ray is moving from the denser to rare medium, there is critical angle is possible, and we can calculate the value of that also. So let's calculate. So if theta is theta c and it is 90 degree, so this is your critical angle. So from here you can just use the Snell's law, that is sine I over sine r. So sine theta c divided by sine 90 will be equal to n2 over n1, and it is 1. So theta c will be nothing but sine inverse n2 over n1. So this is your critical angle. Now see, if theta I incidence is greater than theta c, then there will be total internal reflection. So you can see now at any interface you will see that if ray is moving from 1 to 2 or 2 to 1, there will be two angles exist for the Brewster's angle. We have seen that. But see, there is only one critical angle possible when the ray is moving from the denser to rare medium. So that is the difference between the Brewster's and the critical angle, that there is possibility of two Brewster's angle, but possibility of critical angle is only one. So now I hope that it is clear to you that what is critical angle. So let's move forward and let's see the implementation of critical angle, that is we see in the optical fiber. So in the optical fiber, let me explain the structure first. This is your cladding, and this is your core, and this is your air. So this is your fiber. Inside that there is two medium, that is cladding and the core, where this cladding is nothing but lighter, rarer medium, and this is core is denser medium as compared to this. And this is as well compare means to the air, it is also denser. So n1 is greater than n2, means n2 is here, n1 is here, and outside the optical fiber we assume that refractive index is 1. So what happens here that there is LED or laser, we can just apply any electromagnetic rays or the waves or the ray of light. So that will be at a particular angle. So that is theta a, means this is called the acceptance angle. If this angle is greater than this theta a, then there will be no total internal reflection and there will be no ray passed. Why? Let us see here. When it is moving from the rarer to the denser, so we will see that it is bending towards the normal. And when it is bending towards the normal, then this angle is decreasing. Means it is, let's say, if this theta a is increased from this, then it will be again increased from here also. So if there was the angle theta c, so this another ray which is as greater than angle theta a, that will be less angle here, less than theta c. So when the angle is less than theta c, then there will be no total internal reflection. So we'll say that this is the maximum angle possible at which you will have the total internal reflection. Less than this, there will be exist the total internal reflection, but greater than this theta a, there will be no total internal reflection. So I hope it is clear to you. So that's why we call the theta a as maximum acceptance angle. There will be no TOI greater than this theta a. So we can say that at the core and the cladding, we can say that it is moving from the denser to the rare medium. So we'll see that sine theta c, sine I over sine r you can apply, that will be equal to n2 over n1. And from here sine theta is c is nothing but n2 over n1. So you can find the theta c, and we will see here. So there will be TIR, total internal reflection, at the core cladding interface when the theta is less than equal to theta a. So I told you that it must be less than theta a because this is the maximum angle possible. Now the air core interface, we will see the air and the core interface. So let's find the value of theta a. So see, sine theta a by sine 90 minus theta c, this is nothing but sine I over sine r, that is equal to n2 over n1. So this is your N2, means here as compared to air. So this is your N1 divided by the refractive index of air, that is 1. So N1 over 1 equal to this. This will be cos theta c, and from here you can just find the theta a. How? Cos theta c is under root 1 minus sin square theta c, and sin theta c is N2 over N1. So from here this sin theta a will become under root N1 square minus N2 square. So theta a will be sin inverse N1 square minus N2 square. So this is your maximum acceptance angle, and we also call it as numerical aperture of fiber. So you must remember this, that how to find the value of theta a, and what is theta c, and what is the maximum acceptance angle, and how this works. So now if you know this, so let me tell you one more thing. There is EM wave is coming, or the ray is coming, so there will be some intensity of that ray. So it will be decreased as it is moving inside this optical fiber. So how it is decreasing? So we'll describe that intensity or the power in terms of the P. So P with the Z is decreasing as initially P naught, so it will decrease exponential minus alpha P Z, where this alpha P is nothing but attenuation constant. So here it is in simply per kilometer, means power per kilometer decreasing. But if you write this attenuation constant in terms of the decibel per kilometer, so then this formula will become alpha P Z equal to 10 log P0 divided by Pz, and this is base is 10. So when the attenuation constant is simply power per kilometer, means power per kilometer attenuation or the decreasing power, then it will be this formula. But when alpha P is in terms of the decibel per kilometer, then this will be your formula. So now you can solve the numerical based on this. So now let's see the state of polarization. So we have discussed in the last lecture that there was circularly polarized light. So let's see what is that means. So let's say we have only two linearly polarized waves, that is one in the x direction, one in the y direction, and the amplitude is same, E0, but see there is phase difference of pi by 2. It is cos and it is sine, and delta is same. So we'll see that how they will superimpose. Superimposition says simply it is E1 plus E2. So there are two components. So net component will be under root square of this and square of this. So that will give you EX and EY component. So net component will be AX square plus EY square. So that will give you cos square theta plus sin square theta equal to 1. So from here we'll get this equation. Now see EX and EY, if they will make a circular structure where EX and EY on the perpendicular axis, they will make a circular structure. So that's why we call that as circular polarization, because this is the equation of circle. And now in the circle they can be right circularly polarized or the left circularly polarized, means it can be in this direction or in this direction. So let's see how can you find the RCP or the LCP. So we'll consider at Z equal to 0 the two waves, and we will see that it is left circularly polarized or the right circularly polarized. So at Z equal to 0, this will become Ex equal to E naught cos minus omega t will give you cos omega t, and it will give you sin minus omega t will give you minus sin omega t. So Ex will be this, Ey will be this. Now see here, we will see the different times. So at the initially when this is 0, this will give you Ex will be E naught, and the Ey component will be 0. So initially it is here. So we were here. We have seen that when the time is 0, so initially this will give you x component will be E naught and y component will be minus, means that will be 0. So initially it is here. When the 1/4 time is passed, means omega t will be pi by 2. Then this will give you 0, and this will change to minus E naught. So this is going like this. And again when the time is 1/2, so half time it will give you, means angle is pi. So it will be cos y will be minus E naught, and this will give you 0. So it will be minus E naught and 0. So you are moving like this. So that's why we will call it as the right circularly polarized. And now we'll see the how it is left circularly polarized. So when it is moving like this, then we'll call it as left circularly polarized. So how can we do that? Now if there is this minus sign, means we will say that there is a difference between, means these two will be 3 pi by 2, means initially it was pi by 2, we consider the phase difference. Now if the phase difference is 3 pi by 2, then this will be minus y cap E2. Then what happens, in place of plus there will be minus, and here also, means this will be equation will be minus, and again you will get a circular equation, that's why it is circularly polarized. But there will difference here also, means it will give you sin minus omega t will give you minus sin, and minus is already there, so it will give you plus. So equation will change to this, Ex will be E naught cos omega t and Ey will be E naught cos sin omega t. So now if you check at the time 0, this will give you E naught and this will give you 0. So initially it is here, but at the 1/4 time pi by 2, this will give you 0, and this will give you E naught plus E naught. So this will, you will reshare. Now at the half time it will be minus E naught and the 0. because see, it is cos pi will give you minus, so it will be minus e naught. So x will be minus e naught, and the ey component will be 0. So you will reach here, means x component is minus e naught, you can see, and y is 0. So you are moving like this. So it is left circularly polarized. So I hope it is clear to you how it is RCP and the LCP. We will see. So we have seen that when phase difference is pi by 2 or 3 pi by 2, then EX and EY will be give LCP and the RCP. So now if phase difference is pi, so that means it will be minus E naught cos kz minus omega t plus delta, second component. So they are both are cos, and the phase difference is pi. Then we will see that they both will remain linearly polarized waves. So and when they are equal, means it is not minus y cap, and it is again E naught cos, and it will be E naught cos, and it is x cap and y cap. Then you will get a linearly polarized wave again. Okay, so that's the difference you need to remember. When they are pi by 2 and 3 pi by 2 phase difference, you will get a circularly polarized. But when there is no phase difference, or pi phase difference, or 0 phase difference, then you will get a linearly polarized wave. And see, here we assume that amplitude is same, E naught, E naught, that's why we are getting circularly polarized. But if amplitude is changed, E1 and E2, then you will get EX over E1, here you will get EY over E1, and there is cosine sign. So square will give you EX by E1 square plus EY by E2 square will give you 1, and this is the equation of ellipse. So the whole thing will change to ellipse simply, and here you will get E1 and minus E2 in this way, and it will be again right elliptically polarized, or the left elliptically polarized. So only thing is that it will circle will change to ellipse, other things will remain same, and we'll get the same equation. Only difference is in place of E naught you will get E1 and E2. So that difference you must remember, that how to find the elliptically polarized or the circularly polarized, and when it will be linearly polarized, and what will the phase difference. So I hope it is clear to you now. So let's move forward to a new thing. So we have studied that means we have studied about the potential and the electric field, magnetic field at the constant value, means when they remain same with the time. So we have seen the charge density, current density, and the potential and the vector potential, electric field and the magnetic field at a particular instant, and at a particular position with the when these are not changing with time. But if they are changing with time, then how we can calculate these things? So then we need to find these terms, that charge density at RT and current density RT, and the scalar potential RT, vector potential RT, E and B at R and T. So when they are changing with time, then how can we find the things? So first let's write the Maxwell's equation first. So we know divergence E equal to rho by epsilon, divergence B equal to 0, del cross E equal to minus del by del T, and del cross B equal to mu naught J plus mu naught epsilon del E by del T. So these are our four Maxwell's equation. And again here also, when it is changing with time, so we can write this equation del dot B as B equal to del cross A. So still this equation is valid. Now see, after seeing this Maxwell equation, we can say that here in this left hand side there are 6 variables for E, means 3 variables for E, Ex, Ey, Ez, and for 3 variables for B, Ex, Ey, Ez, and there are 4 equations. So we have 4 equations and 6 unknown here. So if we know V and A, how they are changing with time, means vector potential, the scalar potential, we know how they are changing with time, then we can reduce these equations into 2 equations with only 4 variables. So let's see how can we do that. First we need to write the equations, these Maxwell's equation, in terms of the V and A, and then we will see. So first let's find the B and E. How can you find how they are changing with time in respect of V and A? So we are assuming that we know V and A. So del cross E from this third equation, that is minus del B by del T. In place of B we'll write del cross A. So when you differentiate, it will give you del cross. Now take this to the left hand side, it will give you curl of E plus del A by del T equal to 0. Now from here you can write this is something like curl of some vector, and that vector can be written as the gradient of some scalar. So E plus del A by it is something like del cross A equal to 0, then E is nothing but minus del V. So in place of E, this time you have E plus del A by del T, that is equal to minus del V. Now we know A and V, so from here we can just write E equal to minus del V minus del A by del T. So from here you now find the electric field, how it is changing with time, means you know A and V, how they are changing with time, then you can find electric field also, how the electric field is changing with time. So that's how you can find the E in terms of V and A. Now you also can find the B, that is del cross A. So if you know A, then you can find B. So that's how you can find B and E, how they are changing with time. Now let's write these 4 equations in terms of V and A. So how can we write them? So from this equation del dot E equal to rho by epsilon, in place of E we will replace this value, because now this is E is also changing with time, so we need to replace E with this. So in place of E, we will write this. So we'll get minus del V minus del A by del T equal to rho by epsilon naught. So it will be del cross V, and it will be, means it is take the minus sign outside, so it will be minus minus plus, and this minus go this side, so it will be minus rho by epsilon. So you will get plus here. So del cross V, and it will be del by del T and divergence of A equal to minus rho by epsilon naught. So this is your first equation in terms of V and A. Now let's to find the second equation. We will use this. In place of B, we will remove this B or substitute B with del cross A, and in place of E, we will substitute this value. So let's substitute them. So del cross A, in place of B I have written this. So mu naught J plus mu naught epsilon del by del T. In place of E I have written minus del V minus del A by del T. So now let's just rearrange this and simplify. So this can be reduced to this formula, del dot A minus del cross A equal to mu naught J minus, now you can just multiply inside, it will give you minus, del operator will be came outside, mu naught epsilon naught del V by del T, and this will be plus minus minus mu naught epsilon naught del square A by del T square, second order derivative. Now you will take just this term, and this term will go this side, and this term will also go this side, and this term will go to the left hand side. So del cross A minus mu naught epsilon naught del square A by del T square. Now you will take this minus divergence common, it will give you, means this is also on the right hand side, so it will be give you del dot A and plus this mu naught epsilon del V by del T, and equal to, this will go to this side, it will be minus mu naught J. So this is your second equation. So only two equations will be will be required here. So we have reduced these four equations to the two equations, and here you can see that only variable is V and A. So now you have V that will be in the single, means that will be scalar, that's why it is a single variable, but A is a vector, that's why it will give you AX, AY, AZ. So you have four variables, V and AX, AY, AZ, and there are equations only two. So two equations and the four unknowns. So that is the case. So in the next lecture we will see some example based on that, and what type of question can be asked. So that's all for today. Thank you everyone.